Is it visible, sir? PPT?
One second, sir. Sir, can you please share it again, sir?
Yeah, chat, sir.
Yes, sir. No, it is visible, sir. Thank you, sir.
Okay. One second, sir. Okay. Very good afternoon to all. First of all, let me thank the coordinator for inviting me for this workshop, and a very big thanks to the faculty member who has introduced me. Okay. So, and thanks to the participants too. So today we are going to discuss on solar power conversion and integration. Okay. So the basics of solar power, how conversion is taking place, and how it is integrated into the grid. These are the things which you are going to see today in this session. Okay. So let me move on to the highlights of the presentation. I'll start with, see, when you go for solar power, it will be coming under renewable energy systems, right? So when you want to study about renewable energy system, then we need to know what is the existing non-renewable energy system. That's conventional energy systems. So we'll start with the basics of conventional energy system. Then we will see why we are moving from conventional to renewable energy systems. Okay. Then we'll see there are a lot of renewable energy sources we have. Out of that, we'll just stick only on to solar photovoltaic system. Okay, so we'll see the basics of solar PV system. What is a solar panel? How conversion is taking place? Why the efficiency is very low? Okay, why solar panels are tilted? All those basics we'll see in this one. Then we will move on to the components of PV system. Okay, and what is the position? Because the output of the solar panel depends upon the position. Okay, so what position we need to keep, in which position we need to keep the solar panel, what should be the angle, so all such things we'll see here. And finally we'll see integration. What are things we need to consider when you are integrating this solar panel to the grid. Okay, so this comprises of the basics of solar PV cells and the integration and its integration. Okay, now as we are going to see about renewable energy sources, let's just see a quick glance to what are non-renewable energy sources. Okay, see, from the name itself, it's clear, right? Non-renewable, so they are not renewable energy sources. Okay, so if you see non-renewable energy sources, okay, so mostly they are all natural resources only. Okay, non-renewable, all those things are natural resources only, but they cannot be regrown or remade. Okay, once you are taking, it will be over permanently. Okay, so that's why they are called as non-renewable energy sources. So they are also natural resources only, but they cannot be remade or regrown. Today we'll take, tomorrow also we'll take, but day after tomorrow nothing will be left. Okay, so that's why they are called as non-renewable energy sources. And if you are taking non-renewable energy sources, okay, so very often we will be using fossil fuels, right? Fossil fuels are okay. And if you see fossil fuel, if you take coal, okay, oil and gas. See, what are the fuels we are using mostly? They are coming under fossil fuels, right? Coal means you'll be using for thermal power plant, okay. Oil will be using it for your vehicle, okay, petroleum, all such things. Yeah, petrol, diesel, it's for your vehicle, it's for your aircraft, for your ship, everything will be using that. Then gas, that's a natural gas which we have nowadays. We are using it for vehicles as and for a home also. Okay, so all these things will come under fossil fuel. Okay, because you can't think of a condition without these things, right? Because as far as our country is concerned, 69% of the power generation is from thermal power plant only. So fossil fuel is coming into picture there. Okay, if you see the vehicles on the road, okay, so either they'll run in petrol or diesel or CNG, whatever it is, they'll be coming under fossil fuels. Okay, natural gas, mostly for cooking we are using gas. Okay, so whatever energy we take, most of them are from the fossil fuels. Okay, and why it is called as fossil fuel means because of the fossilized remains of plants and animals. Okay, they have been created, and the remainings of the plants, they've been converted into coal, whereas the animals, they got deposited and they have been converted into oil. That is the history we see. Okay, so these things are called as fossil fuels. Okay. And if you see the fossil fuel, okay, around 66% of the power generation is from fossil fuel worldwide. Okay, not our country. In our country, around 69% of the power generation is from thermal power plant. That is, if you take worldwide, around 66% of the power generation is from fossil fuel. Okay, and as a whole, if you take the energy, 95% of the energy is from fossil fuel only, because see, fossil fuel is not only used for generating electric power, right? Fossil fuel is used for generating electric power. Fossil fuel is used in your vehicles, right? In aircraft, everywhere fossil fuel is used. So if you see as a whole, around 95% of the energy is from fossil fuel only. Clear? So it's very, very tough to replace everything all of a sudden, right? 95% of the energy, if you want to replace it by renewable energy source, means it's really tough. Okay, step by step, they are getting replaced. Okay, so now it's good, right? Because 66% of power generation is from fossil fuel, 95% of the energy is from fossil fuel. Everything is clear, right? It's perfect. Okay, then why we want to move from this? Okay, because it's available. 60 power generation is there. I'm getting power. If I go to petrol bunk, I'll get petrol, diesel. Everything is available. Then why I want to go for renewable energy sources? Why I want to leave this fossil fuel? There are a lot of reasons behind this one. I'll just tell you a few reasons why we are not going for fossil fuel. Okay, the first one is they are not renewable. Okay, they are not renewable. Okay, that means I'll just show you a graph. Okay, this is a graph which shows the availability of fossil fuel, which is all coal, gas, and oil. Okay, as we all know, they have been created from the fossilized remains of the plants and animals. These things came millions of years before. It doesn't mean that last week or last year or last 100 years before they got deposited and today we are using them. It's not the case. Millions of years before they got deposited and now we are utilizing them. Okay, and we are utilizing in such a manner, rapidly we are utilizing them in such a way that by 2100, okay, 2100, this is cold, right? The entire Cold War in the universe will get over. That's the speed at which we are utilizing them. Okay, yeah. Now see, just think of a condition as a country as India is concerned, 69% of the power generation is from coal. Okay, but one fine day there is no coal, means where will go? Clear? So today I'll take coal from here, tomorrow I'll take from some other place, day after tomorrow some other place I need to go. After that nothing will be left off. Clear? And if you see not only coal, if I see gas and oil is this one. See, by 2058 it's given in this graph. So everything within 2100, most of the things will get over. Okay, see how many number of vehicles are running on the road. Okay, they are using petrol, diesel, and gas. So whatever power generation is from fossil fuel only, but they are not renewable energy sources. One fine day, everything will get over. Okay, so as of now, we need to find some alternate fuel which is renewable in nature. That means it should not get over. Clear? Today I'll get that fuel. Tomorrow also it has to be there, and day after tomorrow also it should be available. That's what we want. But as far as fossil is concerned, today is there. Tomorrow also it will be there. But day after tomorrow we don't know, because after a few years things will get over. So we need to find an alternate source or alternate fuel which is renewable in nature. Okay. So that is the first thing, availability of fossil fuel. Okay. Then next one, if they are available, okay, as in that fossil fuels are available, okay, still they'll be creating a lot of issues. Okay, so the first one is with their availability. Okay, so availability also is an issue. The second one is if they are available also, there are a lot of issues with fossil fuels. Okay, and the first thing is that pollution. That's the biggest problem we have with fossil fuel. Okay, pollution is one thing. Clear? If you just see the thermal power plant, how much emission is occurring. If you just see the picture of a thermal power plant, just see near the chimney, how much emission is coming. Okay, so huge emission will be there from the fossil fuel. Okay, not only if we go for electric power, right? If you see the vehicles which are running on petrol or diesel, how much emission is there? That's why nowadays we want pollution certificates and all, because they'll be polluting a lot. Okay, so availability, okay, let me on one side. Even though they are available, they'll be creating a lot of problems. Okay, pollution, lot of health hazards they'll be creating. So a lot of issues are there with fossil fuels. Okay, not only this one. Okay, pollution is one big issue with the fossil fuel. Okay, then you have another one is the greenhouse effect or global warming is also there, because see, burning of fossil fuel is the main reason for the global warming that you could have studied, right? If I am burning a fossil fuel, what will happen is that it will be emitting a lot of gases, and all these things will get accumulated. Okay, all these things will get accumulated in the atmosphere. That's what's happening. So in general, what will happen is that the radiations of the sun, most of the radiations from the sun will come to the earth. Okay, a part of the radiation will penetrate to the earth and it will go. Few radiations are absorbed by the earth and few radiations are reflected back by the earth. Okay, so since the earth is observing some radiation, okay, the temperature of the earth is moderate such that we can live. Okay, that's why the temperature is medium, around 20 to 30 or something, so that we can live. If that is not happening, means it will be very cold earth. Okay, since it's observing, it's warm and we are okay to live here. Okay, and some are reflected back. Okay. But if these gases are getting accumulated in the atmosphere, what will happen is that these reflected radiations won't go out. They will be reflected back again to the earth by these gases. Okay, so again they will come to the earth. Again they will increase the temperature of the earth. That generally we will call it as global warming. Okay, so burning of fossil fuel is the main reason for global warming, and this ozone layer, all these things are getting destroyed, right? So all these things are because of these fossil fuels. Okay, and one more thing, these fossil fuels are getting deposited in the atmosphere, right? I mean, these gases are getting just forming a layer in the atmosphere. When it rains, what will happen is that they'll dissolve in the rain and it will come to ground as acid rain. Okay, so that will affect the lot of living small organisms in the earth. Okay, so pollution is there, global warming is there, a lot of health hazard is there, acid rain is there, and availability is there. Those are all the big problems with fossil fuel. So we need to find one alternate fuel which is renewable in nature. That is first one, which does not create any pollution. That's what we want. Okay, and it should not emit anything. There should not be any emission from this fuel. So it should not be a cause for the global warming. There should not be any acid rain out of that. So all these things we are expecting from the renewable energy sources. Okay, so these are the effects of fossil fuels. Okay, clear. Now let's move on to the renewable energy sources. So you have seen these non-renewable means they cannot be remade or replenished again. So what are renewable then? See, from the name itself you can understand, right? Renewable, they can be remade again. That for example, if I'm taking a solar radiation, today I'm getting sun, solar radiation is there. Tomorrow also it will be there. Day after tomorrow also it will be there, right? As long as sun is there, things will be there. We can't expect a date where there is no sun and all. If there is no sun, nothing is left out, right? So always we'll be getting this solar power. Okay, and if you take wind, as long as sun is there, the difference in temperature will be there, so wind will blow. Okay, so everything will be renewable. Everything will be there always, sustainable there. Okay, so these are called as renewable energy sources. They'll be available throughout. It doesn't mean that today I'll get solar power and tomorrow nothing will be left over. This is not the case. Always you'll be getting that power. Okay, so that's how they are called as renewable and sustainable energy sources. Okay, and if I am taking renewable energy sources, a lot of things are there. Wind is there, solar is there, geothermal, biomass, a lot of people are there. Okay, but as far as our country is concerned, or normally we'll be concentrating only on to wind and solar. Okay, because as far as our country is concerned, mostly we'll be concentrating only on to this. Okay, in that I'll tell about solar. Okay, if I'm taking solar. Okay, see, normally when we are talking about solar, okay, just let me start with the solar. Okay, when you're talking about solar, the first thing which will come into mind is that the cost. Okay, the cost of power generation, because we need a huge panels, lot of place we need a lot of converters, all these things. So whenever we are talking about solar, the first thing which will strike in our mind is about the cost. It's true that the initial cost of all these things were high initially. That means before 5 years, okay, if you want to generate 1 megawatt of power from a solar panel, it takes around 8 crores rupees. But now for 1 megawatt of power generation from the solar panel, it's taking only 3 to 4 crore rupees. That's all. The cost has came down to 50%. And in future also this will come down. Okay, so the cost is not an issue now. Initially it was an issue that the cost is high. Now it came down. Okay, and if you see the renewable energy scenario, okay, so just 10 years before, the total installed capacity in our country was around 160 gigawatt of renewable energy. Okay, so by 2030 it is expected to be 830 gigawatt of renewable energy sources. Okay, and if I take solar, just before 5.5 years it was around 2.6 gigawatt only. Now it is around 34 gigawatt of installed capacity is there by solar, and by 2030 it is expected to be 300 gigawatt. Okay, so this is one of the very promising solution for power generation, because it's clean, it's renewable, it's green, it's available always. All these advantages are there with solar panel. Okay, now let's move on to the I'll just tell you a small comparison between a fossil fuel and a solar panel. See, first of all, what we are seeing, just one example. If I want to generate 1 megawatt of power, okay, just that is example, 1 megawatt hour of power I want to generate. I am using it coal. So what we are seeing is that when I'm burning fossil fuel, the first thing is it will have a lot of emission. Okay, emission is there. Then the second one is it will increase the temperature. So global warming, both will be there. These numbers are taken from reference papers. Okay. Whereas the same 1 megawatt of power, if I'm generating from solar, okay, you can see there is no emission and there is no increase in temperature. This is what we want from a renewable energy source, right? This is what we expect. First one is it should be renewable, so solar is renewable. Second one is there should not be any emission. You can see there is no emission from the solar panel. The third one is that global warming is there with fossil fuel, whereas when you go for solar panel, there is no global warming. Okay, so this is one source where all the issues we have with the fossil fuels will be eliminated. Okay, and this will show what is the difference between what is it, solar and once again solar power generator and others. Okay, so here you can see it includes both renewable as well as non-renewable. Okay, it includes both renewable as well as non-renewable. You can see coal, oil, gas, all these things are there which are non-renewable. You have hydro and wind which are renewable. So this side is a combination of both renewable and non-renewable, whereas this side is only solar, because that's the difference between them and this. For example, if I'm taking a thermal power plant, first one, coal. Assuming that considering a non-renewable energy source, thermal, okay, if I'm taking a coal of a thermal power plant, the fuel which you give is a coal, that is a fuel, and the output which I want is an electric power, right? The fuel which you give on this side is coal, and that side I will be getting electric power as an output. Okay, so but directly by giving coal, we won't get anything here, right? So coal will be crushed, powdered, it will be ignited, right? It will be ignited, then it is used for boiling water, then water will boil, it is converted into steam. Okay, then steam will run a turbine, the turbine will run a generator, generator will give electric power, right? That means in between the source and the output you have a lot of stages, and most of them are mechanical stages, right? So a lot of losses will be there in between these stages. Okay, burning this one, igniting this one, boiling water, converting it into steam, that steam is running a turbine, turbine is running a generator, then there you are getting an output. So you have a lot of intermediate stages where a lot of power loss will be there. Okay, if same case, if you go for a nuclear also, only thing is that the way in which the heat is produced is different, right? There I am igniting the coal, I am generating heat, whereas here just by using nuclear fission reaction, heat is generated, right? That's the difference. Remaining all processes are the same. Okay, if you go for renewable also, if you take wind also, okay, so wind will be just striking on the blades of your nacelle or turbine. Okay, so then your blades will rotate. That is connected to a low speed shaft, because the speed of the wind is very less, right? It's connected to a low speed shaft. Then you'll be having a gear mechanism which is used to increase the speed. Then that is connected to the high speed shaft. Then that is connected to the rotor of a generator, by which you'll be getting electric power. So from the wind, to the electric power, you have a lot of intermediate stages, even if you go for a renewable energy source like wind also. Okay, lot of losses are there. Whereas solar is the only one in this category where the solar radiation is directly converted into electric power. Solar radiation will directly fall on the solar panel. It is converted into electric power and will take it. Maybe the magnitude and all will change accordingly, but there we'll be using a lot of power converters whose efficiency is always more than 95%. So that is not an issue. Okay, but here it is direct conversion. There is no intermediate stages. That is why the difference is given here. Solar is on one side, which is a direct conversion of electric power, solar radiation to electric power, whereas all the other which are given in this picture, they have a lot of intermediate stages. By that only electric power is generated. So a lot of power loss will be there in these kind of power conversions. Okay, so that is a difference. Okay, now let's see what is actually happening in a PV cell. Okay, PV means it's a photovoltaic cell, which is mostly made up of silicon, right? It's made up of silicon. Okay, so what happened is that, okay, whenever the radiation from the sun, see, when you go for a solar, right, you have two things. One is light, the other one is heat. Whatever we are talking about power generation is because of the light. Heat is used for some other applications also. At the end, I'll just show you one slide with all applications of solar. Okay, not only for power generation, there are a lot of other applications also. Here, light will fall on the solar panel. Okay, what will happen is that three things will happen here. One is that the part of the light will be passing through the solar panel. Okay, pass through the solar panel, light will go. Second, when a part of light is absorbed by the solar panel, and a part of the radiation is reflected back by the solar panel. So three things will happen. Part of light will be absorbed, a part of light will penetrate and go, a part of light will be reflected back. So it doesn't mean that all these things are converted into electric power. Only the observed radiations are converted into electric power. That is the case. Okay. Out of these three, reflected, observed, and which is going inside, only the observed radiations are converted into electric power. That means even though if you have a lot of solar radiations which are falling on your panel, only which are all observed will be converted into electric power. Okay. So only the observed light generate electric power. That is the case with solar panel. So it doesn't mean that all the radiations, whatever radiations which is falling on your panel is converted into electric power. That is not the case. Only the observed radiations are converted into electric power. Okay. I'll show you the spectrum of this is actually a solar spectrum. This is categorized with respect to the wavelength. Here we will start with. I'll tell you why I'm showing this one, because next one will be with respect to this one. Okay, so lower wavelength in the top and longer wavelength, shorter wavelength in the top and longer wavelength at the bottom. That's how this graph is given. Okay, so you have a lot of radiations coming from the sun. We'll start with the gamma rays. Okay, then you have X-rays, then you have ultraviolet rays, infrared is there, microwave, radio, all people are there, right? But not all these radiations are converted into electric power. Only a few radiations are converted. Okay, so one side is wavelength. So shorter wavelength to longer wavelength. Shorter wavelength starts with gamma, then X-ray, then UV radiations, then microwaves will be there. The visible radiations, all these things will come, right? Okay. Now let's see which are all the radiations which are converted into electric power. Okay. So the thing is that, okay, I'll just I'll tell you, as per Planck's law, okay, as per Planck's law, what he has stated is that, okay, so the energy of the incident, okay, the energy is inversely proportional to wavelength. Energy is inversely proportional to wavelength. That is important. Okay, it's not directly, it is inversely proportional to wavelength. That means the radiations with the shorter wavelength will have more energy, and the radiations with longer wavelength will have less energy. Okay, see, we have radiations ranging from shorter to longer, right? A lot of people are there inside the spectrum. So, but not all these radiations have the same energy level. Okay, so the energy level depends upon the wavelength. Shorter wavelengths have more energy, and longer wavelength radiations will have lesser energy. Okay, for example, ultraviolet rays, okay, or gamma rays, all such things are shorter wavelength. They have more power, more energy, whereas red, infrared, microwave, radio waves, and all are having longer wavelength. So you can understand that they'll be having very, very less energy. Okay, so now it's clear. Okay, so everyone is having their own energy. Okay, so what is the minimum energy level required to emit an electron? Okay, then we need to know. Okay, because in between a lot of calculations were there. Okay, so the thing is that If all these radiations are converted into electric power, then it's well and good, right? It's perfect, but that won't happen. Okay, yeah. So that won't happen. Okay, so I'll tell you what is that. So now we need to know. See, all the radiations are there. They have their own energy level. So there should be some specific value of energy level, right? So that is by Planck's equation. So the wavelength required is 1110 nanometers. So that is the actual wavelength whose energy is used for emitting electron from a silicon. That's the value we need. Okay, clear? So I'll just show you a graph. Then I'll come back to this. Okay. Now this is 1110 he has given, right? So that is the wavelength, because a lot of calculations are there. They understood that this is a wavelength which has a minimum energy to emit an electron. Okay. So 1110 will come 1110. It will be coming somewhere here. Okay. So that is separate. That, sorry, assuming this is a straight line. Okay, so 1110 is the one which we need. Okay, now see, as per Planck's law, okay, so higher wavelength will be having low energy. Okay, that means if we go beyond this 1110, 1200, 1300, 400, 500 and all, wavelength is increasing whereas the energy is decreasing, right? So they don't have the energy to emit, generate power. So this side is eliminated now, because they have more wavelength, less energy. So minimum is 1110 needed. Okay. Now let's come this side. Okay. So now the graph is from 0 to 200 to 1100. So initially you can see ultraviolet radiations, right? You know, ultraviolet radiations very, very rarely they will be coming to Earth, right? Because most of them are blocked by the ozone layer and all. So they are also not considered. So this is range now. Okay. Clear? So ultraviolet radiations also go. This side after 1110 everything will go. So only this is a range of radiations which are converted into electric. See, the spectrum is drawn from 200 to 2200. But the radiations ranging from 400 to 1100 or around 1000 only is converted into electric power. So out of the total radiations we have, only a very small part is converted into electric power by silicon material. That's why generally we used to tell that the efficiency of solar cell is very, very less. It's around less than 20% theoretically. Because out of all the radiations which are coming inside the panel, only these very small spectrum, very, very small value from 400 to 1000, that's all, will be converted into electric power. Remaining all will go waste. Okay, so that's why its efficiency is assumed to, its efficiency is very, very less. It's less than 20% theoretically. Okay, but nowadays a lot of researches are going on to improve the efficiency of this one. They are trying to coat it silicon carbide. They are trying to do it. Okay, they are trying to go with some nano materials. And recently there were one article, because I'm not sure, because still now I'm not able to get the details. There was one article which is telling that there was one photovoltaic cell with 6 junctions. This is one junction normally. 6 junctions. They have better efficiency. Like this, a lot of work is going on in this area to improve the efficiency. Okay, so theoretically it is around less than 20% for a silicon cell, but when you're going for a lot of other modifications, then the efficiency will be improved. But it doesn't mean that all the radiations will be converted. Only they are able to convert only a part of the radiation into electric power. So that's the efficiency is very less. Okay, now let's see the position of solar panel. Okay, so it's clear that solar panel, whenever solar radiation is falling in the earth, solar radiation is falling on your panel, it is converted into electric power. That is clear. Okay, but can we keep a solar panel in any position? Okay, we can't keep in any position, because when you see, when you go for some laboratory experiments, often we used to see that these solar panels are kept it in the floor, or they are kept it in the top, roof, at in horizontal position. So if you keep it in a horizontal position, it will work and it will give some output, but that is not the actual output which the solar panel is intended to give. It will give very less output if you put horizontally. Okay, so I'll tell you why the solar panel. See, this is tilted. The solar panel is tilted actually, tilted by some angle. It's not horizontal, or it is not vertical also. It is tilted by some angle. These are all the practical graph which is from NIT Silchar. Here we have these many panels. They are all tilted. Okay, you can see all these panels are tilted. Okay, so you need to understand that solar panels are not horizontal, they are tilted. I'll tell you why it is tilted and at what angle they have to be tilted. Okay, I'll just take a plain sheet. Okay. Yeah. Okay. So let me start with see if I take our Earth. Okay. Assuming this is our Earth. Okay. So in the top we have northern hemisphere. In the bottom you have southern hemisphere. In the middle you have equator, right? So three things that generally we used to study in history. You have northern hemisphere in the top, southern hemisphere. I mean, as per this one, northern hemisphere is there, southern hemisphere is there, and then in the middle you have equator. Okay. So we have sun here. Okay. Assuming this whole shape of sun, earth, and all are like that. Okay. So when sun is emitting a lot of radiations, you can see that the radiation is from the sun is directly falling on the equator, straight, right? It's perfectly falling on equator. Whereas when it comes to north and south pole, I mean southern region, it's falling at some angle. They are not directly coming. You can see, right? So directly sunlight will fall on the countries which are near the equator. Whereas when you go for northern and southern hemisphere, they'll be falling with respect to some angle only. Okay. Assume that I am keeping a solar panel horizontally near the equator. Near the equator, I am placing a solar panel horizontally. So if you keep a solar panel horizontally in the equator, no issues will happen. The entire radiations will fall on your solar panel because directly it is falling. Okay. So the countries which are near to the equator, they don't want to tilt it. Directly solar radiation will come. Whereas assuming that in India, we are in northern hemisphere, right? So in northern hemisphere, I am putting horizontally. Okay, I'm putting horizontally. If you put horizontally like that, only a very less portion of the solar radiation will fall on your panel. Okay, so this is southern. I'm putting it horizontal to the plane. Okay, you can see only a part of the radiation will fall on the panel. Remaining all these things go. Okay, you won't get the maximum output if you put horizontal like that. Okay, now let's come to next point. Assuming that the same Earth, same Sun, northern hemisphere, southern hemisphere. Okay, so instead of this one, I'm tilting like this. Instead of putting horizontally, I'm tilting the panel. Okay, then what will happen if I'm tilting it? All the radiations will fall on your panel. Same as the equator. Now, all the radiations are falling directly on the panel. Okay, in southern also I'll tilt it. Then lot of radiations will. So in order to make the radiations fully fall on your panel, it has to be tilted. Okay, if you are putting horizontal, only a part of the radiation will fall on your panel. Now, in which direction it has to be tilted? You can see in northern hemisphere it is tilted towards the south. In southern hemisphere it is tilted towards the north. Okay, just opposite. Okay, northern hemisphere it is tilted towards the south, and in southern hemisphere it is tilted towards the north. Okay, for as far as our country is concerned, we are in northern hemisphere, right? So whatever panels we have in a country, it will be tilted towards the south. Okay, it should face the south. If you are keeping in north, means just opposite to this one. Okay, whereas radiations will be there on your panel. So always, as far as our country is concerned, we need to tilt it towards the south. Since we are in north, just opposite direction we need to tilt it. Okay, hope it's clear why it is tilted and in which direction it has to be tilted. Okay, and the angle at which it is tilted is called as a tilt angle. I'll just show you here. Okay, the angle at which it is tilted is called as a tilt angle. You can see here, this is a tilt angle. Okay, the angle at which it is tilted is called as a tilt angle. Okay, and this tilt angle will change with respect to regions. It will change with respect to country. It will change with respect to regions. It will change with respect to states. Everything. Okay, it's not fixed. Okay, I'll just show you an example here. Okay, let me take our country. It depends upon the latitude. Okay, the latitude at which place is. See, for example, this is with respect to our country. Okay, so you can see they have divided the entire country into 4 zones. Zone 1, 2, 3, 4. If it is zone 1, it is in the top, right? North. Clear? They are zone 1. You can see Jammu and Kashmir, Punjab, HP, Uttarakhand, everything is. You can see the tilt angle is 30 to 36 degrees there. That means their latitude is 30 to 36 degrees. Okay, so the tilt angle is 30 to 36 degrees. Whereas the same solar panel, if I come to South India, it is zone 4. Okay, you can see the tilt angle is from 12 to 18. See the huge difference. There, the same country, if I put it in zone 1, that is northern states, the tilt angle is 30 to 36. Whereas the same solar panel, if I am putting in southern India, it should be from 12 to 18. So the tilt angle changes with respect to the country, with respect to the regions, with respect to the state, everything to change. It's not fixed. Okay, so this is the angle at which you need to tilt. For example, if it is Karnataka, Tamil Nadu, Andhra Pradesh, Telangana, Kerala, Goa and all, the tilt angle will be between 12 and 18 degrees. You can see these states, when you go, the tilt angle will be very less, whereas if you go to some other state, the tilt angle will be more. Okay, like this. Zone 1 has more tilt angle. Okay, so hope you understood what is tilt angle and what should be the value of tilt angle. Okay. Now I was just skipping few things. Yeah. One more thing is that, okay, clear. So sun is okay. Always it's moving in one direction to other direction. That's what we have studied in history. But see, for example, this is a destination. Assuming this, 1 second. Assuming this is a destination of the sun and this is a source, always it will start from source to destination. That's what we are saying, right? But the thing is that so the starting is the same and the ending is also the same. Okay, same direction. But the angle in which it is going. See here the example is given. In June 21, the path followed is like this. Whereas in December 21, the path followed is like this. Anyway, starting is the same and ending is the same only. Whereas the path is changing with respect to the day. Clear? June 21, this much angle, whereas December 21, this much angle difference. Okay. So these all are needed when you're going for forecasting the output of a solar panel. When you're forecasting the output of the solar panel, you need to know what is the tilt angle. That means you need to know in which state it is, which place it is. So through the latitude, we'll calculate the tilt angle. Then with the which day you want to calculate, that day will give you what is this angle that we need. Okay, clear. All these are needed when you want to go for the forecasting of the solar power. Okay, so just understand, everywhere when you go from place to place, the tilt angle is different, and from season to season, this angle is also different. So when you want to go for a perfect design, you need to take care of each and everything. If you want to go for a perfect design of a solar system, solar panel system. Okay, yeah. And you can see, right, see winter tilt angle is different and summer the tilt angle is different. Okay, because in winter, see, always it will be from one place to other place only, but the direction, the angle in which it is moving will be different in each seasons. So according to that, the panel has to be shifted if you want to get the perfect output. Okay, so all these things you need to take care if you want to go for the installation of a solar panel. Okay, so that is a tilt angle. Okay. Now let's move on to the connections of solar panel. Okay, so we have seen a solar panel. Okay, what is a solar panel? How it is generating electric power? All such we have seen. Okay, and if you see solar cell, a solar cell means a single one. A single device is called as a cell. Okay, the thing is that a single cell can give from 0.5 to 0.6 volt. That's all. A solar cell can give just 0.5 to 0.6 volt. That's it. But this is not enough for any applications, right? It's very, very rare to find an application with 0.5 to 0.6 volt, right? We can't get an application for this one. We'll be having application with 20 volt, 30 volt, 300 volt, 400 volt like this, right? So, so if you want to increase the voltage level, I'll be connecting them in series. I'll connect all these solar cells in series. That is called as a module. For example, if I'm connecting 72 modules in series, I'll get around 36 volt, assuming that each cell is 0.5 volt. Or example, if I'm connecting 60 cells in series, I'll get around 30 volt. Like this, depending upon the requirement, you can connect them in series. So that is called as a module. Okay, it depends upon the number of the output voltage needed. Okay, if you want more voltage, connect more of them in series. Less voltage means connect less of a number of solar panels, solar cells in series. Still, this 36 volt and 30 volt are not enough for some other high power applications. Okay, clear? There I need 200 volt DC. I need 300 volt DC. Means again these solar modules are connected in series. Okay, so that is called as a solar panel. Okay, so solar cell, it will be connected in series. It is a module. Modules will be connected in series. It is called as a panel. Okay, so through which I'll get whatever DC voltage I want. Solar cell give 0.5 to 0.6 volt. I'll put a module which can give n number of voltages depending upon the connection. Then all these modules are in series, that is called as a panel. That will give you the actual voltage level you want. Okay. And now if I want to increase the current level, again I'll be connecting them in parallel. That is called as an array. So solar cell is a basic one. Series connection is a module. Series connection of module is a panel, and parallel connection of the panel is called as an array. This is how the entire structure is. Okay. Yeah, this is how. Same thing is given in other form. Start the cell. Series connection is module. Again, series connection it is panel. Then parallel connection it is array. These are the things. Depending upon the requirement, it's very rare chance to go for a cell. Okay, but you can go for module, can go for panel, and you can go for array depending upon the requirement. Okay, so this is how they will be connected. Okay, and this is how the output voltage. See, assuming two solar cells is ideal in this case, because it's very tough to get semiconductor devices with ideal characteristics, right? And if you go to power electronics, you would have studied that we can't get two diode with identical characteristics. No MOSFETs are there with identical characteristics. All such things are there. Practically, there will be a lot of difference in their characteristics. But assuming an ideal case where I have solar panels whose voltage is once again, whose voltage is 0.6 and current is 0.8. Ideally, everyone, all the sources are having, solar panels are having 0.6 volt and 0.8 amps. So if I connect them, two of them in series, you can see they are connected in series. So 0.6 plus 0.6, 1.2 is the voltage and 0.8 is the current. Okay, 0.8 is the current and 1.2 is the voltage. Okay, clear. And in the same two cells, if I'm connecting in parallel, in parallel, you will have the same voltage, but the current will get added as 1.6. So depending upon the requirement, you can connect them in series or parallel. Finally, all these combinations, this one and plus this one, they are connected in parallel, so that you will get 1.2 volt here and 1.6 amps here. Like this, either by connecting them in series or by connecting them in parallel, you can get the desired voltage. This is for an ideal case. But practically, you can get whatever voltage or power you want. That's how they are connected in series and parallel. Okay. And this is actually the characteristics of a solar panel. This is cute. The spelling is wrong. Okay. Yeah. So if you take a solar panel, okay. 1 second. Let me have a cup of water and come. 1 second. So this is the characteristics of a solar panel. Okay. So this is a IV characteristics, current versus voltage. So when you go for the characteristics of a solar panel, they'll be giving with respect to some specific conditions. Okay. If we see the data sheet of a solar panel or whatever graphs of a solar panel, they'll be giving this with respect to certain conditions. That means for at constant radiation or at constant temperature only, this is the graph. If the radiation is changing, the graph will be different, or if the temperature is changing, the graph will be different. Most of the case you can see with the 1000 watts per meter square radiation and 25 degrees centigrade. That's how they'll be given. Okay, and finally they will tell that this graph is for this condition. Okay, and if that is changing, then the output will change. Okay, so here the temperature is kept constant, assuming that some value they are kept constant, and they are varied the radiation. Since you can see 1000 watts per meter square means this is the voltage. When it is coming to 800 current, for 600, 400, you can see. So as the radiation is varying, you can see the current is changing. Clear? So that practically happen in the solar panel, because if I take a day, morning radiation will be different, 11 o'clock it will be different, afternoon 12 o'clock it will be different, evening 4 o'clock it will be different. So for different radiation, a solar panel will give different type of output like this. Okay, whereas voltage will change, but it's not that much. Okay, whereas if this graph is for 100 watts per meter square irradiation. So the first graph is for a fixed temperature and variable irradiation. This graph is for a fixed radiation and variable temperature. You can see at 10 degrees centigrade, your voltage is like this. At 25 degree, it is like this. And you can see at 70 degree, it is like this. Okay. So as the temperature goes on changing, the voltage will come down. Okay. So it doesn't mean that if you have a lot of radiations and low temperature, heat is there, you will get more output. If heat is more output, will come down. Okay. So it doesn't mean that if you go to some countries where Norway, Sweden and all, right, the temperature is very less, whereas they will have enough radiation, so the output will be more. Whereas when you go to some places where you get more radiation and more temperature, means the output will change. Okay, so it doesn't mean that more heat is needed. If temperature is more, output will change. If radiation is changing, also output will change. Okay, so that is the problem with the solar panel. That's why they are volatile in nature, because radiation is not fixed as far as the day is concerned, because it's coming from the sun, right? So morning time it will be different, afternoon it will be different, night will be different. Okay, so as time is going on, the radiation is changing, so the output will automatically change. Current and voltage will be changing here. Okay, like that. Okay, see, when you take it's a solar panel is DC, right? Solar panel is DC. Okay, so power is just the multiplication of voltage and current. That's how we are taking it. Okay, so you have two curves here. One is IV, that is between current and voltage. Other one is PV, that is between power and voltage. Okay, so if I am taking the IV curve, okay, so let me take one point here. Okay, so this is the current and this is the voltage. So it's a DC. So if I multiply these two, I'll get one power, assuming it is P1. Okay. Let me come to other point here. Okay. This is P2. You can see here the current is the same approximately, whereas the voltage has increased. So P2 will be more than P1. Okay. P2 will be more than P1. Okay. And let me take here. This is P3. So current is slightly reduced, whereas the voltage has increased to the max, increasing, right? So P3 is still more than P2. Okay, so power is going on increasing. P1, P2, P3 is going on increasing. But let me come to this point. Okay, see, voltage is reaching its maximum value, whereas the current is reduced to certain value. This is P4. So P4 is less than P3 now. Clear? Initially, P1 we got it. P2 is found to be more than P1. P3 is found to be more than P2. Now we can see P4 is less than P3. Okay, that means there is some point in this graph where if you multiply the voltage and current, you will get the maximum power. So that point is called as maximum power point. Okay, so that point is called as a maximum power point. Okay, I think this one somewhere here. Okay, once again. Okay, so this point is called as a maximum power point. Sir, am I audible there? Hello.
Yes. Yes.
Okay, since there is no response, I need to ask. Okay.
Yes.
Okay. Yes. Okay, sir. Thank you. So this point is called as maximum power point. Okay. So the thing is that only one point is there in the graph. Okay. So that is the only point where you will get the maximum power. Okay, because P1 is less, P2 is more, P3 is more. If you expect that P4 is more, P4 is less. Clear? So there will be one point in the graph where when you multiply voltage and current, you'll get the maximum value. That point is called as maximum power point. And the voltage corresponding to it is called as VMP. There is a voltage corresponding to maximum power. Okay, and current is IMP. Okay. So when you see the specifications of the panel, you can see they will give what is VOC, what is ISC, what is VMP, what is IMP, everything for a particular radiation and temperature. Okay. See, if this is only one point in the graph, means we can understand this is a point and we can operate it according to that point. Okay, but this point will change with respect to temperature and radiation, because you seen, right? See, this graph, current graph, okay, was changing with respect to radiation, and the voltage was changing with respect to temperature. Okay, so for a particular radiation and temperature, this is a graph, this is one point. Okay, but when the radiation is changing, this point will change. Clear? So this maximum power point is not constant. It will change with respect to radiation and temperature. So for each and every value of radiation and temperature, we need to operate in its maximum power point. That means we need to find what is the maximum power point. If it is only one value, means we can identify that value and we can use in that always. But it is changing with respect to the irradiation and temperature. So we need to find what is the value. We need to track it. Okay. So the techniques, the technique is called as maximum power point tracking. So the point is called as maximum power point, and the technique which is used to track it is called as maximum power point tracking technique. Okay, MPPT. Okay, and there are a lot of algorithms for that. You used to have a hill climbing algorithm. That means incremental conductance is there, and mostly perturb and observe is used. Okay, then voltage method, current method, and nowadays you can see a lot of people are using optimization method to find what is the maximum power point. So like this, a lot of things are there, a lot of algorithms are there to find the maximum power point. And nowadays we are getting inverters and DC DC converters. They are having inbuilt technique, inbuilt MPPT inside. Okay, clear? Okay, so this is maximum power point, and the technique is also maximum power point tracking. Okay. Yeah. Clear. Okay. Now let me tell you two more basic things. Then I'll go on to the components. Okay, so blocking diode. Okay, so this is used in solar panel. So the reason is that when I'm taking a solar panel, okay, so during daytime you'll have plenty of solar radiation. Okay, since you're having plenty of solar radiation, you'll have output from the solar panel and it will charge the battery. So current will flow in this direction. Okay, at night. Okay, at night, what will happen is that you don't have solar radiations, right? Since solar radiation is not there, there won't be any output from the solar panel. So the potential of the battery will be more than the potential across the solar panel. So current will start flowing in opposite direction now. Okay. So in daytime, when solar is so radiation is available, the output will be there from solar panel, which will charge the battery. And when there is no output from the solar panel, that is when at night time or evening time when it is dark, there is no output from the solar panel. So what will happen is that the potential battery potential will be more now, right? Because it is charged. The other thing is it's just a thing now. There is no source for that. So current will flow in opposite direction. In order to avoid that, they'll be using one blocking diode here. So you can see the direction of the diode, right? It will allow always current will flow only in this direction. Reverse direction, current won't flow. So only when the solar panel is working, the current will flow from the panel through the diode to the battery. Whereas when there is no output from the solar panel, the diode itself is reverse biased. Okay, so you don't allow reverse power flow. Okay, that is why it is called as blocking diodes. You can see each and every panel will come with these blocking diodes. Okay. So during sunshine, as long as voltage produced by the panel is greater than the battery, charging will take place. That is the usual thing. Okay, and at dark, that is when there is no sunlight. Okay, so it will flow in reverse direction. Okay, so which leads to the discharging of the battery. In order to avoid that, we'll be having a blocking diode which is connected in series. So the direction of the diode, you can see it will conduct in only one direction from the panel to the battery. So that is the function of the blocking diodes. Okay. And another one diode is there, which is called as bypass diode. See, bypass diode means actually there are a lot of solar things which are connected in series, right? You are saying, right? Cell, module, panels, they'll be connected in series. But in some situations, the output of one panel may go low. For example, if there is any shading on that panel, assume that the solar panel is kept near a tree or a building. Okay, when some shade is falling on one panel, they are connected in series. So one panel shading is falling means the output in that panel will be less, right? Clear? Or if some dust is accumulated on the panel, or if anything is there on the panel such that the radiation is not exactly falling on the panel, means the output of that panel will be less. Whereas all of the panels will be conducting. That will create a non-uniformity. So at that time, what they'll be doing is that they'll just bypass that panel. So this diode is called as bypass diode. So if this panel is not working, or if any partial shading is there, then this panel, then it will go through the diode and it will go. So now flow will be bypassed through that diode. That is why it's called as a bypass diode. Okay. So when one or two panels are shaded, this is called as partial shading. Okay, and others are illuminated, then the output of them will be very less. So they'll be just bypassed through a diode, and remaining all will be working. This is called as bypass diodes. So you'll be having two diodes. One is called as a blocking diode, another one is called as a bypass diode in a solar panel. Okay. Now let's come to the next part. Okay, so solar panel is cleared. Okay, solar panel is done, perfect. We have seen that whenever light is falling on the solar panel, it is converted into electric power. I am getting electric power, right? But simply if we have a solar cell, we can directly connect it to the load. Yeah, just maybe very rarely there are some applications where you can connect it to the load, but most of the applications we can't directly connect it to the load. There power electronics is needed. Okay, power converters will come into picture when you want to connect a solar panel to the any load. Yeah, without power electronics is very tough. Okay, so core of a system is PV cell only, but along with PV cell you'll be having a converter which is used for the transferring of the power. Okay. Clear? Just for the efficient PV system and as an interface to transfer generated power to the grid. Because see, if you want to transfer it to the grid, obviously I need an inverter because whatever output I'm getting from a solar panel is DC. So surely one inverter will come into picture if you want to connect it to the grid. Okay. Okay. So PV, I mean power electronics plays a very, very vital role when you go for renewable power generation. Okay. It's used for maximum power point tracking. MPPT, we'll be using this one. Then DC to AC inverter. I'll just show you a diagram and I'll tell you where they need it. Okay. Grid synchronization. There is one concept called a grid tied inverter is there. So that means it has the ability to synchronize with the grid. So whatever we have, we need power electronics. Without power electronics, we can directly connect this solar panel to the load or the grid. Okay. By using power converters only, we can achieve all those functions. Okay. So this is one typical output. Okay, this is a practical output which we took it from Vellore VIT. When I was there in VIT, we took this output from there. Okay, you can see right from morning to evenings, from morning early morning 1 o'clock to 6 o'clock there is no output, and after 8 o'clock in the evening 6 o'clock there is no output. In between only you are getting output from a panel. See, and this output is also not stable. Okay, you can see at 7 o'clock the output is different, 12 o'clock you are getting maximum output. So each and every time the output is different, right? It's very tough to connect such kind of things directly to the load. That's why they are called as volatile or they are intermittent in nature. We don't know what output they will give at what time. Okay, clear? And okay, this is with respect to the day, clear? If I see with respect to the season also it is changing. The same solar panel, the output will be different in summer season, it will be different in winter season. The same panel will give different output in autumn and spring seasons. Okay, so see how the things are going on. Okay, that means I have, for example, if I'm having a thermal power plant, okay, I have a coal as a fuel. If I give this much fuel, this much output I'll get, that is known to us, okay, by the calculation. If I have any other sources also, you know the fuel given and how much output it will give also, it's known. Whereas this is a thing where we don't know what will happen. Where suddenly when cloud is coming, the output will change. When it is raining, the output will change. When sun is shining nicely, the output will change. Clear? So temperature will change the output, irradiation will change the output, climate will change the output, everything will change the output of this one. Clear? So it's very tough to connect such kind of sources directly to the load. We need to go for power conversion techniques in between. Okay. Yeah, if you see the components of a power system, solar PV system, solar array is the basic one, right? That is the one. Without that, other components are not needed if you don't have that. So solar array, I'll just list out. Charge controller, which is used to control the charging and discharging of a battery. Because when you go for a battery, it should be charged at a constant level and it should not be discharged below a certain level. You should not overcharge the battery. All such things control has to be there with the system. That's why you need a charge controller. Okay. Later, you know the function of RESISG. When you go for a very huge solar PV system, a lot of protective equipments will be there. Okay. Battery is there if you want to store the power, because solar won't be available at night, right? If you want to get power, then I need to go for a battery storage. Okay. Then next one is inverter is there. See, solar power is DC, right? If you want to have only DC load or a battery, means I can directly use it. Whereas if I have an AC load, I want to connect to the AC load, means I need to go for an inverter. Even if I want to connect to the grid also, I need to go for an inverter. And remaining all as usual for a system, you'll have meters are there for reading. Okay, then you need protective equipment, all such things. So just if you take solar system, it doesn't mean that solar is the only thing. It is one part is solar panel, whereas when you know all such things are there inside your solar PV system. Okay. So this is a simple example if I take, right? If you take PV, okay, see there is no inverter, there is no grid, nothing, just simply DC load. PV is there, a charge controller is there to control the charging of a battery, then battery is there. Okay, clear? So DC load. Okay, so that means whenever solar power is there, power is given to the load and part of power is utilized for charging the battery. And when there is no solar output, then the battery will give power to the load. Okay, this is the simplest one. And you can see a perfect example also. This came in newspapers, right? I think it's in Bangalore. Okay, that means old lady, she is using this technique for his cooking his corn. Okay, because if you want her to boil the corn, she need air. Okay, to blow it. So you can see a solar panel here. Okay, you can see a battery backup and DC to DC charge controller here, and you can see a fan here. Okay, so simple, same type of application. See how far these things have reached now. Clear. So this is one typical application of a solar panel without much converters inside. Okay, simple application. Okay. When you want to go for a perfect system, then see this is the one which we actually have. Along with that, we need these many number of components depending upon our requirement. If I have only DC load, I need only DC to DC converter. And if I want, I can give for a battery also. But if I want to give it this to an AC load, okay, then surely you need to have an inverter. And if I want to connect it same to the grid, then it should be a grid connected inverter. Okay, so this is our solar system. Okay, solar panel power converters. Okay, this is how solar power is there, charge controller is there, inverter is there, DC load will be there, and AC load will be here. Okay, this is actually a typical graph of this is taken from the book. Okay, how a charge controller is working. Okay, see as far as the battery is concerned, okay, thing is that we need to charge whenever it is needed. Okay, then it should not be charged beyond certain level. It should not be discharged below certain level. And when battery output, battery capacity is very less, load should not be connected. So a lot of conditions are there when you go for a battery. So the charge control is a device which will take care of all these functions in a battery. Okay. For example, VR is a voltage regulator. Okay. That means this is the maximum value to which the battery has to charge. Okay. So if this value is already set, means so until this value is reaching, the charger will connect the source to the battery. When this value is reached, automatically the source will be disconnected. Okay, that means it don't allow the battery to charge beyond this value. Okay, then VRH means the same voltage regulation hysteresis value. Okay, clear? The thing is that now I have connected to this. See, I have a battery. It is charging from a source. The battery has reached the maximum value, so I have disconnected it from the source. Okay. Now I have connected to the load also. It started discharging. So when I have to connect back to this source, so that is given by this threshold value VRH. Okay. So when the battery capacity is reaching this value, you can see automatically recharging will takes place. Okay. So this is with respect to the user, they can set anything. Okay. And next one is LVD, low voltage detection. So that means the battery should not be drained below a certain level, right? This should not go to 0% and all. So this is a value which is already set. So once this value is reached, automatically the load will be disconnected. Okay, when the battery capacity reaches this value, automatically the load will be disconnected. Okay, and now assume that the load is disconnected and the battery is charging now. When it has to be connected to the load again, because initial case the battery is fully discharged and it is connected to the source for charging now. So when I can connect the load, that is given by this hysteresis value. So the capacity value reaches this one, means automatically it will be connected to load again. So all these functions are governed by a charge controller. That's why charge controller is very important when you go for these kind of techniques. Okay. And this is a tracking. Okay. So tracking in the sense, assume that I have a solar panel. Okay, we have seen solar panel is kept in some angle, tilt angle is there. It's not kept horizontal. It is kept vertical, not vertical. It is some angle tilted. Okay, so angle there, all such things are there. Okay, but you see the sun, it is not stationary, right? It is starting from one side and it's ending in another side. That is as per the history we have studied. but something is rotating, those things and all you forget. One fine morning it will be on one side, and that the same day evening it will be on another side. But a solar panel is stationary on one direction only. If that is the case, means the output will be very less. Same as that of the first graph. You can see here. Okay, you can see here. Sorry. Yeah. Okay, the first one is without any tracking. Okay, you can see here the sun is moving here. Okay, sun is moving in one direction. Okay, but you can see the output also. Output is going to the peak in the afternoon. Okay, but whereas when you go for if you want to get the exact output, all the output from the solar panel, sun radiation, then we need to track the panel. Track the direction of the sun, and we have to move the panel according to the direction of the sun. That is called as tracking. Because in morning sun will be at one side, and in the evening it will be at another side. Clear? So we need to track the direction of the sun, and according to that it has to move along with the sun. That is called as tracking. And in case of tracking, there are two methods. One is called as single axis tracking, and the one is two axis tracking. In the second graph, you can see, third graph, you can see it is single axis tracking. Single axis tracking means it can move from west to east and east to west. That's all. Okay. So along with the sun, this solar panel also track that direction, and it will move along with that, but in only one direction, west to east and east to west. That's all. Okay. But you can see, so sun is going from one direction to another direction, it's there always. Whereas depending upon the date and season, the angle in which the sun is moving will change. Okay, the angle in which the sun will change. That means it's one direction itself is not enough. We need to go with north and south direction also. So if it is able to track all the sides, then it is two axis tracking. Okay, that means when you go for no tracking, panel will be fixed there. One axis tracking or single axis tracking means along with the sun's direction, it will go with that. Okay, but it's only one direction, either east to west or west to east. Okay, north and south won't come into picture. But whereas depending upon the season, the angle in which the sun is moving will change. Direction will be the same, whereas the angle in which it is moving will change. So if you want to track that also, then you need to go with that direction also. So if north, south, west, east, all the directions are coming into picture, then it is called as two axis tracking. You can see the graph. Without tracking, you can see the output is there only during the peak. Only in the afternoon. Whereas the second one is two axis turbine. You can see around 94% of the radiations are falling on the panel. It's not the efficiency of the panel. 95% of the radiations will fall on the panel. Whereas in the first case, it's only 64% will fall on the panel. Remaining all will go off. Okay, this is actually the tracking, but this is a bit costly. So the thing is that if you want to go for tracking, then you need to see how much profit you can get, because tracking needs motor, sensors, and all, right? If tracking, before tracking, I'm getting 100. For example, I'm getting 100 rupees, assuming in as rupees. Before tracking, I'm getting 100 rupees from this one. After tracking, I'm getting 110 rupees. But the tracking system cost is 200 rupees, means then it's no use of going for tracking. Okay. So if before going for tracking, just you need to see that if that is output you are getting is cost effective or not. Those things we need to go, we need to see, then we need to go for such kind of tracking systems. Okay. And this I'll come at the end. Okay. So when you go for converters, okay, so the first one we have is a DC to DC converter. Okay. So as far as DC to DC converters, it is used for converting DC to DC. It's either fixed DC to variable DC or variable DC to fixed DC. And if I'm taking DC to DC converter, if you want to step up the voltage, then I'll go for a boost converter. If you want to go for step down, we'll go for buck converter. If both the operations are needed, then it is buck boost converter. Okay. But the advantage of buck boost converter is that both can be done. Either step up or step down can be done depending upon the requirement. Whereas buck means only step down and boost means only step up. But one problem with buck boost converter means the range is limited. For example, if I am using a buck converter, see ideally, okay, see practically it will be different. Ideally 0 to 1 is a duty cycle, right? So 0 to 100% is the duty cycle can be used for buck operation. If I use only boost converter, 0 to 100% of the duty cycle used only for boost operation. But whereas when you go for buck boost converter, 50% is used for buck and remaining 50 is used for boost. That means the range of buck is half and range of boost is also half. That is the problem with buck boost. but we can get both the conversions in that. Then a lot of other regulators are also there. CUC regulator is there. Then quadratic boost converter is there. Loop converter is there. Lots and lots of converters are there in the picture. People using. Okay. Then the next converter we have in a solar panel is an inverter. Okay. Inverter, because if AC load is there, then we need to go for inverter. If I want to connect it to the grid, because in your rooftop solar panels are there, very big solar plants are there, everything wants inverter, right? So if you take inverter, three main categories are there. One is micro, other one is string, and one is central. I think in between that you have some multi-string or something also. I just put in general: micro inverter, string inverter, and central inverter. Three types of inverters are there. Depending upon the application, you can go for any type of inverters. Okay. So this is micro inverter. See, micro inverter in the sense, each and every panel has an inverter. So this panel has an inverter, this panel has an inverter, every panel has an inverter, and the output is connected like this. Okay. For low power applications, we can go for micro inverter. So micro inverter means each and every panel has an inverter connected to it. Okay. So output will be taken and given to the load. But for low power application, we will go for micro inverter. So the disadvantage of this inverter is that each and everything needs an inverter. So it's very costly. It's costly, and a lot of wiring is needed because these many outputs has to be connected and taken. Okay. But the main advantage of this one is that, see, suddenly if I want to increase the capacity of the system, I just want to add only the panel because inverter is coming along with the panel. Clear? See, for example, assume that in my home I have an UPS. Okay, I have a battery and I have the UPS. Okay, inside UPS you have an inverter, right? UPS system has an inverter. Suddenly I want to increase the capacity of this one. I'm putting one more huge battery inside. So surely you need to change the inverter also, because inverter capacity will be different. Now it is increasing, right? You need to change the inverter also because I have changed the capacity of a battery source and all. Whereas as far as this is concerned, if I want to increase the capacity, add one more panel, that's all. Because panel is already coming with an inverter, so I don't want to buy any inverter or anything. Okay, so increasing the capacity is not an issue, just going and adding, that's all. And one more very important advantage of this micro inverter is that, see, this is an inverter. So as far as a solar panel is concerned, we need to operate it in maximum power point. Okay, so here you can see each and every panel has one inverter. That means that inverter will operate at the maximum power point of that panel. Okay, so 1, 2, 3, in this diagram you have 6 panels, right? So each and every inverter works on the maximum power point of that corresponding panel. So everything will work on maximum power point only. Okay, so there is an advantage. Individual maximum power points can be used. Okay. Yeah, this is a micro inverter. Okay, so single PV panel itself has everything inside. Okay, inside. And you can see it is very less power capacity. Okay. The feature is that it has one inverter per module, so best MPPT capability of all configurations. Because each and every inverter, module has an inverter. Each and every module has an inverter. So each and every module has can be operated on its maximum power point. Clear? That is advantages. That is the biggest advantage of this micro inverter. But cost is very bit higher, and range extension is not an issue. Just add a number of panels. That's all. Okay, clear? And this is mostly used for small scale PV systems. Okay. Small scale PV system, you can see the power capacity is up to 300 watts. So for small scale systems, you can go for this micro. See, from the name itself, it's clear, right? Micro inverter, so small size inverter. Okay. Now, let's go for a string inverter. Okay. Here, in this example, 5 panels are connected together and one inverter for this entire string. So this is called as a string. Okay, so for one string, one inverter. In this string, you have 5 panels are connected together. So only one inverter is needed for such kind of things. Okay, so the main advantage of this is that, okay, number of inverters needed is very less. See, when you go for micro inverter, each and every panel needs one inverter. Here, number of inverter needed is very less. Less cabling is needed. Clear? But you see, the problem is that if I want to increase the capacity, if I am adding 2 more solar panels here, Okay, if I add 2 more solar panels here, then I can't use this inverter, right? Because the capacity is increasing now. I need to change the inverter. If I want to increase the capacity, then some change is needed here. And one more thing, you can see 5 panels are there and only one inverter is there. One inverter can operate on only one maximum power point. See, let me number the panel 1, 2, 3, 4, 5. So the maximum power point of this one is P1, P2, P3, P4 and P5. Since you have only one inverter, it can operate either in P1 or P2 or P3 or P4 or P5. It can't operate in all the power points. Clear? So the maximum power point utilization of MPPT is very less in this one because any of the panels maximum power point only it will take. Okay. Yeah, this one you can see string of PV panels are there. Okay. And string of PV panels are there and one inverter. Okay. Is string economy only one inverter per string. Okay. Yeah. So, but the thing is that compared to central inverters, this is advantageous, but compared to micro inverter, this is not advantage because micro inverter can operate in individual power points, whereas this can operate in the power point of a string only. Okay, and the thing is, it's mostly used for. I think let me say last one. It's used for medium scale PV systems such as rooftop and residential. So what are we are using? Okay, rooftop systems and residential systems. We can go for this string inverters. Okay, medium scale PV systems. Okay. And the last one is the central inverter. Actually, this diagram has all the three. Okay. Okay, this diagram has all the three. You can see here. This is a module. Okay. Clear? And this is the inverter. So each one has one inverter. Each one has one inverter. So this is micro inverter. You can see here number of strings are connected to one inverter. So it is string inverter. But you can see here all the solar panels are connected to only one inverter. Clear, you have number of inverters here, number of inverters, but a centralized inverter means only one inverter. The output of all the strings are connected to that inverter. Okay, the output of all the strings will be connected to that inverter. So that is actually a centralized inverter. The capacity is very high. Okay, so the advantage of this one is that you don't want to go for how much cabling. Okay, you need only one inverter, so the control is very easy. Okay, cost is effective because there we need n number of inverters. Here only one inverter is needed. Cost effectiveness is there. Okay, you don't want to go for much cabling or wiring as far as this is concerned. But the problem with this is that if the inverter is failing, then the entire thing will go off. Okay, because only one inverter you have for the entire solar arrays. Okay, so if some problem is there with the inverter, then the system goes off. Okay, and one more thing is that you can see, for example, here 6 here for 3 PV panels, 1 MPP. Here 1 panel, 1 MPP, 1 panel, 1 MPP. Here 3 panel, 1 MPP. Here 1, 2, 3, 4, 5, 6 panel, only 1 MPP, right? So the output will be very, very less in this case because out of, see, as per this diagram, we have 6 panels, right? After these 6 panels, you can operate in the maximum power point of only one panel. Only one value it can work. So the output will be very less. Okay. Yeah. So it's just a single 3-phase voltage source inverter to connect the whole PV plant to the grid. Okay. It uses one inverter to connect the whole PV plant to the grid. Okay. And one thing is that it is a simple structure because I have only one inverter. All the wirings will come from the, what is that? Solar panel and it will join on the inverter. So only one control system is needed. Lot of advantages are there. Okay. Simple structure, single control system. Okay. Lot of sensors and all are there. Okay. Very less number of sensors and all are there. Okay. But the problem with this is that, okay, MPPT algorithm is there for a whole system, not for individual panel. So you can't get the maximum output from that. That is one problem with this. Okay. And mostly this is used in large scale. So micro inverters are used for very low power applications. So for medium power applications and residential rooftop and all, we'll go for string inverter. And large scale PV plants means we'll go for central inverters. Okay. And another one is a multi-level inverter is also there is a initially we had inverters, right? Normal inverter, 2-level inverters. Then the research has gone to the multi-level inverters, right? When you take multi-level inverters, a lot of advantages are there with multi-level inverters. Clear? The switching stress is reduced. Switches can be operated at lower frequency and reduction in harmonics is there. All are the advantages of this one, right? So switching stress is less. Okay, harmonics is less. The output waveform is much closer to the sinusoidal waveform, and you can get more output voltage when you connect multi-level, right? More levels you can get in the output. So a lot of advantages are there with the multi-level inverters. Okay, and yeah, now the thing is that can be operated lower switching frequency with less harmonics and switching stress. Okay. So output waveform quality is better because it's as the number of levels increases, it's approximately will go near the sine wave. That is the advantage. Okay. So most of the industrial and commercial applications, this MLIs are used. So why can't we use such kind of technology in PV? That is also there. Okay. So there are few inverters which are used in PV. They are using NPC, neutral point clamped inverter, cascaded high bridge inverter, flying capacitors, MMC, all such things, all these categories of multi-level inverters are now used in solar panels too. Okay, but if you see the reference papers or journals and all, most of them are just sticking on to two, NPC and CH. We can see few papers with others also, but most of them will be going for cascaded H-bridge and neutral point clamped inverters. Okay, but still, rather than using a normal inverter, this is advantageous because less harmonics, less switching frequency is needed. Okay, and less switching stress also. So now this is another area of work. Okay, the same PV system can be in which the multi-level inverter can be incorporated. Okay, so this is another application. Okay. Now, if we see the categories, okay, or the classifications of wind, we'll be classifying it into two mainly. One is off-grid, other one is on-grid. Okay, off-grid means it's a standalone. On-grid means it will be grid connected. Okay. So off-grid or standalone system and on-grid or grid connected system. If you say off-grid means it's simple from the meaning it's understood. It's off the grid. Or standalone, it has the ability to stand alone without having a support from the grid. Okay. So here, as far as off-grid is concerned, what it will be there is that you'll be having solar panel, that's a source. Okay. Then you have an inverter, then battery backup, all such things, and it is giving supply to the house. Okay. So there is no grid involved in that. If needed, you can go for a diesel generator also. If needed, you can go for a diesel generator. Apart from that, it's nowhere related with the grid. There is no grid connection, so it is off-grid or standalone system. Okay. Next one is on-grid means it will be connected to the grid as well as it will be connected to the PV panel. As long as you are getting output from the panels, we will be using it. And when the output of the panel is less or which is less than the demand which I have, I can take power from the utility. This is called as on-grid system or grid connected system. Okay, so solar panels will be there, inverter will be there, which is connected to the house. Okay, then if power from this one is very less, then power is allowed to go from here. Okay, so this is on-grid system. Okay, but you can see this is bidirectional. That's important concept. Okay, this is bidirectional. I'll tell you what is bidirectional, why it is bidirectional and all. Okay, let's come to this. Okay, excuse me. So assuming that I have a solar panel, I have a rooftop solar panel here. Okay, a rooftop solar panel is there. Okay, and here consider that I have a load of 1 second. I think when animation is coming, it's not. So, okay, in this one itself, I'll use this. Okay, consider that I have a solar panel with me. Okay, I have a solar panel with me, and one fine day, assuming this today, the time is 3:30. The connected load is okay 2 kilowatt. Okay, connected load is 2 kilowatt. Okay, and my solar panel is giving 1.5 kilowatt. Okay, so from the grid I will take 0.5 kilowatt. Yeah, this is what generally on grid will do, right? So the connected load now is 2 kilowatt. Okay. So solar is 1.5 kilowatt it is generating, and from the grid the remaining 0.5 I'm taking. This is a grid connected system. The same. Okay. Suddenly what happened is that with the load of same load of 2.52 kilowatt, the solar itself is generating. Solar itself is generating 2 kilowatt. Okay. So then the grid should be equal to 0 because I'm not taking any power from the grid. Okay, so whatever power which is needed, whatever demand is there, that is actually generated by the solar itself. So I don't want to take any power from the grid. So first case I'm taking 0.5 kilowatt from the grid. Second case I'm just not taking any power from the grid. Let's come to the third case, the same load as 2 kilowatt. But now the solar is generating 2.5 kilowatt. So the connected load is only 2 kilowatt, okay, but the solar is generating 2.5 kilowatt. So where this 0.5 will go or what will be done? So in this case, this can be given back to the grid. So this is the grid. I can give the remaining 0.5. Up arrow will tell that it is given back to the grid. That means if your demand is less than the generation, solar generation, we can take from the grid. If the solar power generated is more than your demand, the excess power can be given back to the grid. Okay, so at the end of the month, okay, assume that there are a few places where once in 2 months they'll take the reading. There are a few places where once in a month they'll take the reading. Assuming that at the end of the month, okay, he has consumed 120 units. Just example, in the end of the month he has consumed 120 units, and in the end of the month, this by using this excess power which is sent back to the grid, he has given back 80 units to the grid. Okay, clear? He has consumed 120 units from the grid, and say certain times the solar power output will be more, so he has given back 80 to the grid. So what he need to pay is the remaining 40 units coins he has to pay. So that means the net difference only he has to pay. Okay, so this concept is called as net metering concept. Okay, when the power generated from the solar panel is more than the demand, the excess power can be given back to the grid. So okay, so that actually is an incentive. Okay, clear? So that is called as net metering concept. Okay. But for net metering concept, you can't use a single normal meter. It should be bidirectional meter, because when the output of the solar panel is very less, power will flow from the grid to the load. So power is flowing in one direction as we have here, right? Whereas when you go for net metering, when the output of the solar panel is more than the load, extra power has to go back to the grid. Okay, so then it is bidirectional. Then that direction is opposite. That's why you need a bidirectional meter. This is actually, you can see both the arrows are there, so that meter should be bidirectional. Okay, clear? So this concept is called as net metering concept. Let me come to this one. You can see here. Okay, so first that green color is coming. Okay, so that is going to the load, and the remaining green is going to the what is that, post or the pole. That means when power is more than the demand, excess power is going to the grid. That's why the green color is there. When power demand is more than the solar generation, the excess power will be taken from the grid. That is coming as red color. This concept is called as net metering concept. Okay, here you need bidirectional meter if you want to go for net metering concept. Okay, this is one of the important concepts when you go for solar panel. Okay, but here as far as net metering or a grid tied inverter, this is a grid tied inverter because you are connecting this to the grid. Okay, you are connecting this to the grid. So as far as grid tied inverter is concerned, we can't use a normal inverter for this purpose. That is different. We need to have different inverter. Okay, see, for example, I'm having a UPS at my home. Okay, I'm having an UPS at my home. It is connected to the battery backup. So whenever there is no power, this output of the battery will be inverted and it's given to the load. That's what generally UPS will be doing, right? But the thing is that this UPS doesn't want to see anything. The UPS is designed in such a way that, sorry, the inverter I'm particularly taking. The inverter in the UPS is designed in such a way that it has to give this much voltage at this frequency. That's all. Apart from that, no other thing is there inside. Okay, input is there from the battery, switching is already fixed. Okay, so this is the output frequency of that voltage, and this is the voltage level which you need to generate. That's all. Clear? So it doesn't see anything else. Depending upon the program, to already what is there in that, it will convert and it will keep. Okay, whereas when you go for such kind of applications, you can't do that. You can't use the normal inverter, because normal inverter is intended only to give power to the load. With a normal inverter, you can't supply power to the grid. Okay, so for this one, we need grid tied inverter. Grid tied inverter means it should be tied to the grid. That means the grid tied inverter, or the inverter which is used in the net metering concept, should have the ability to synchronize with the grid. Because if you want to supply power to the grid, it should be synchronized, right? When you're doing a lab example, I mean experiment for machines or transformers, synchronization is needed, right? So same as that, if you want to connect it to the grid, or if you want to give back to the grid, you need to synchronize with the grid. Okay, so that means the voltage, depending upon the grid voltage, the inverter has to adjust the voltage. Depending upon the grid frequency, the inverter has to adjust its frequency. Then only you can supply power back to the grid. Clear? So synchronization is much essential when you go for grid tied inverter, and grid tied inverter has an inherent capability to go for synchronization. Okay, whereas when you go for a normal inverter, there is no option for synchronization. You'll just give the voltage and with the desired frequency, that's all. But this grid tied inverter has the ability to synchronize with the grid. When grid frequency is changing a little bit, the inverter frequency will also change. When the grid voltage is changing a little bit, the output voltage of this inverter will also change according to that. That's how it is synchronized. Okay, so that's the difference between a normal inverter and a grid tied inverter. Okay, when you want to go for this net metering concept, this you need to go for grid tied inverter. Normal inverter won't work in this. Okay, yeah, grid tied inverter. And this is actually, these are all taken from journal papers. This is how this is working. Okay, the concept is working. This is actually the solar panel. Okay, see, considering that, assuming that I have a load of 2 kilowatt. Okay, so solar panel has generated 2.5 kilowatt. So 2 kilowatt will go to the load and 0.5 kilowatt will go to the grid. This is what the net metering concept is. That's the grid tied inverter will do. That means 2.5 kilowatt is a generation, 2 kilowatt is the load, remaining 0.5 kilowatt is given to the grid. This is normal, it's working fine. Everything will work in this. But now one condition is that when grid is off, what will happen? Okay, now suddenly there is no power from the grid. Okay, but the power generated by the solar is more than the demand. Whether it is the remaining power is given to the grid or not, that is a big issue. Because assume that I have a grid tied inverter which is connected to the grid. Okay, so in the grid, when they will normally cut power means if they have maintenance or if they have any fault. Normally during faulty conditions, they'll turn off the grid and they'll do the repair work, or if they have any maintenance, they'll do it. So while going for maintenance work, what they will do is that they'll simply switch off the supply from the grid, and they will work on the transmission lines or transformers or distribution lines and all. Okay, so that is a usual thing. They'll switch off and they will work on that. Okay, but when you have a grid tied inverter concept like this, okay, assume that this is a network which is connected like this. Okay, so here a lot of people are working on the transmission line. They have switched off the supply from here and they are working on the transmission line, assuming that there is no supply. But this is a grid tied inverter concept. Okay, here you can see 2.5 kilowatt is a generation, so remaining 0.5 will be given to the grid automatically now. But the grid is off and people are working on the lines. Okay, so this will create a lot of safety issues. Okay, because automatically power will go to the grid. The people are working on the grid, and when they are in transmission line or distribution line or transformer, they will get affected. Okay, because power is still coming from the net metering concept of solar panel. They were the thought that they switch off the grid, but power is coming from another direction now. So in such conditions, so grid tied inverter is designed in such a way that whenever there is no power from the grid, it will turn off the inverter. That means the inverter output will be reduced, turned off. Whenever there is no power from the grid, the output from the inverter to the grid will be 0. Okay, because it has a ability to synchronize, right? Whenever the grid is off, okay, the frequency, reference frequency and reference voltage will be 0. So when this is sensing 0 frequency and 0 voltage, automatically it will stop its function. Okay, so when the grid is off, the power should not go to the grid. Okay, so this mode is called as anti-islanding mode. Okay, whenever there is a power cut or grid is off, this net metering concept should not work. Okay, this is called as anti-islanding scheme. And a lot of areas are there to work. Clear? See, consider this is another example. These are all taken from papers. Okay, consider that. See, when you go for malls and all, clear, they have generator backup, right? Now, assuming that I have a solar panel, I have a diesel generator backup, and I have a what is that? Grid. Consider that the grid power is off now. Okay, diesel generator and solar are working. So again, with net metering concept, if the load is due 2 kilowatt and if the generation is 0.5 kilowatt, what as per the concept, the 0.5 has to go to diesel generator inside. Clear? Because if it is synchronized, what the inverter will do is that if the power output is more than the power demand, the excess power will be given to the source. Okay. Here instead of grid, you have a diesel generator here. Okay. So what happens is that the 0.5 kilowatt will be going to the diesel generator. That will create a lot of issues again. So when you go for grid tied inverter, a lot of concepts are there like that. Okay, anti-islanding mode. If diesel generator is connected, how the control has to be. All such things are areas of work. Okay. And if you see the application of PV panel, okay, so whatever we have seen is just the power generation, okay. But if we take solar radiation, it has light as well as heat. What we are using for power generation is a light radiation, okay, but heat is also used for a lot of applications. One is solar water heating, but here the concept is that, see, it is not directly converted into electric power and is heated. See, you have water heaters at home, right? You will be switching on the supply. You will have a heater coil that will get heated, water will get boiled or heated. That is the thing. Whereas when you are assuming there is a solar water heater, the first thing will come into your mind is that solar panel, it is converting solar radiation into electric power. That is used for heater. That is not the case. When you go for solar water heating, the heat from the sun itself is directly used for heating the water. There is no conversion of electric power. Okay. And here also solar distillation, there is no conversion of electric power. Heat is directly used for this application. Okay, solar pumping, solar drying, solar cooking. So this is what you have seen till now, electric power generation. Here solar so radiation is converted into electric power. Whereas when you go for refrigeration also, now we have in air conditioner, solar based air conditioner. Okay, there also we can think that the solar is used for generating electric power, that is used for an air conditioner. That is not the case. The heat from the solar energy, that's from the sun, is utilized for some boiling some ammonia or something refrigerant. That's the function there. So apart from this electric power generation, for most of the applications we see here, the heat is used. Okay, it's not converted into electric power. The heat itself is directly used for the application. Okay, and air conditioning. Okay, you can see nowadays we have lots of applications with a solar panel. You can see street lights are running with solar panel. You have a lot of other applications. And you can see the Narmada Canal project, right? Floating solar panel. You can see solar panels above the ground. Canal level. So it has two functions. One is it will convert solar radiation into electric power, and second one is that it will avoid the evaporation of water. So that's the advantage. And you can see one more thing with the solar. You can see in India's first airport, okay, Kochi, Nedumasheri. You can see that it's full of solar panels. Clear? There is no other backup. Okay, only solar panels are used for running the entire airport. See, just think that just the solar panel is used for lights. Then solar panel is used in their home. Then it is used for generating power, giving to the grid. Rooftop solar panel. Now we see solar panels used for running the entire airport itself. And I think 1 or 2 years before we have seen one. This also, right? One entire flight is running with solar panels, only on solar panels. Okay. So this is one of the area where a lot of works are going on and a lot of applications are there. Okay. But when you go for till now what I have seen is okay, but there, if you want to integrate to the grid, there is a lot of other issues also when you go for solar panel. The first one is they are volatile in nature. Okay, they are intermittent in nature. So connecting them to the grid is not that much easy. Because, for example, leaving the solar panel, leaving the renewable energy issue, I have hydrothermal, nuclear and all. Okay, when I'm going for dispatch, when you go for load dispatch center, they'll be going for dispatch of generations, right? They know if I give this much input, this much output, there will be there from the thermal power plant. According to that, seeing the demand, they can give the dispatch for the generators. They will generate power. Whereas when I'm putting solar panel into picture, okay, suddenly solar panel output will change. Suddenly with radiation change, output will change. With the climate, output will change. Okay, with partial shading, output will change. Everything will change in output. So just assuming that I have this much capacity of solar panel, depending upon that, if I go for dispatch, sudden fine time one day the output of solar panel may come down, so we need to go for extra generation on the other side. So believing these solar panel, and if you go for a dispatch, then it's very tough, but still a lot of work is going in this area such that you can also, so that's why nearly all 100% of the power generation cannot be replaced by these renewable energy sources, because see, they are volatile in nature, their output may change at any point of time. Okay, 100% if you believe in this one means there won't be a chance that you'll be there without power also. Okay, again, if you see, not only solar, wind is also, the output will be changing with respect to time when the wind speed is changing. All these things are intermittent in nature. Okay, and another thing is that harmonics. Okay, see, whatever renewable energy sources we study, everything will come with power electronics only. If I take solar, it has a DC n number of components you have seen, right? You have a DC to DC converter, you have inverter. Whenever you have a power electronic switch inside, then harmonics will be there automatically, right? So lot of harmonics issue will be there when you go for these renewable energy sources. Okay, so integration is a problem. Harmonics is another issue. So a lot of issues are there with but still we hope that in near future all such things will be eliminated, because when you go for a smart grid, right, when you are going for smart grid, so one of the important concept of smart grid is distributed generation, DG, right? So when you are using DG, the advantage is that the generation is near the load side. Okay, so the generation voltage is very less, that's very less voltage is needed. Whereas if I want to transmit now, then we need to go for high voltage generation, or we need to step up and transmit it. Whereas when you go for smart grid, DG is an integral component. Since it is generated near the load side, the voltage level has to be very less, so it is advantageous. And thing is, all the generation is near the load side, so the transmission losses will be reduced, distribution losses will be, all such things will be reduced with distributed generation. Okay, so this one and more and more when we need to avoid the using of fossil fuel, so more and more renewable energy thing has to be come into picture. But this renewable energy has these drawbacks also. Okay, issues with intermittency, harmonics, all such things are there. But still, we'll be having a lot of new technologies in future which will eliminate all such things. Okay. Yeah, all these things. Yeah, flex more and maximum power point tracking. All such things are there when you're going to go for this renewable integration. Okay. So that's all from my side. Now I'm not sure whether the chat is enabled for questions or not. If you have any questions, you may ask now, or if you're not able to ask now, you can put a message. Surely I'll reply you in WhatsApp also. Okay. So now it's open for questions. If a question is there, you may ask. If you're not able to ask the questions, I just gave the mobile number also. Feel free to put a message in my WhatsApp. I will reply for the questions. Sir, it's to the coordinators now.
Yes. Yes. Participants, if you have any queries related to the topics sir have discussed, you can unmute your mic and raise your queries. Yes, I think we don't have any doubts, sir. Jai Krishna, sir.
Sir, good evening, sir. Sreejith, sir.
Yeah, good evening, sir. Very good evening, sir.
Thank you very much for accepting your request and presenting webinar for participants in our STTP, sir.
Thank you, sir. Nice to meet you all.
Your webinar is very nice and informative and very useful for the people who are doing research in renewable energy sources, sir. Thank you very much, sir.
Welcome. So they are welcome to ask any questions at any point of time. My contact is there already given.
Okay, sir. Thank you, sir. Thank you very much.
Thank you, sir. Nice to meet you.
Yes, sir. Good afternoon to one and all. Honorable Secretary, sir, Honorable Principal Madam, most value invited guest, convener, co-convener, fellow faculty members and participants. It's my immense pleasure to propose vote of thanks for this session resource person, Dr. Sreejith, sir. Yes, Sreejith, sir. I am on behalf of St. Peter's Engineering College and the entire team extend my heartily vote of thanks to today's resource person. Dr. Sreejith sir has covered topics from different types of renewable energy sources, efficient generation of electrical power by considering different parameters like tilt angle, irradiation, location, etc. For a PV system. Based on PV panels like series and parallel connection of cells and VI characteristics. Sir has discussed, and Sir has briefed on blocking diode and bypass diode, and Sir has detailedly explained the degree of tracking with the animation provided by the Sreejith sir. And then Sir, in the next phase of his presentation, Sir introduced different components of a PV system, working of a charge controller, brief on MPPV techniques, and different converters like microconverter, string converter, and central converter. And then Sir briefed on off and on grid PV systems and net metering system and grid tied inverter. Then moving on, Sir discussed applications of solar PV system, and in the end, Sir concluded his lecture with challenges in renewable energy integration. Thank you, sir. Thank you for your wonderful lecture on this present session. In spite of your busy schedule, thank you for accepting, sir.
Okay, sir. Thank you.
Yes.
Welcome.
Okay, sir. Yes, participants, we are going to share a feedback link in your WhatsApp group. Please fill the feedback link. And in the last day of STTP, we are going to have a test regarding the concept which we have discussed. So the scoring at the 60%, greater than 60% is essential for the test. So we are going to share the test link in the last day of STTP, and filling the daily attendance and feedback link is also essential. Yes. So we are going to meet in the next session.
Attendance of 80% is mandatory, sir, for all participants. Please join the sessions in time. Okay, sir. You can end Gopi.
Yes.